In the previous video, I introduced the limit comparison test for improper integrals. In this video, I will write down a formal proof for the theorem. First, a quick reminder of what the theorem says. I begin with two functions f and g, and I assume they are positive and continuous from a real number a to infinity. And I assume that the limit of the quotient, as the variable goes to infinity, exists and is a number, which is positive. Then the conclusion is that the improper integral from a to infinity of f and the integral from a to infinity of g must be both convergent or both divergent. I assume you have already watched the previous video where I introduced the theorem slower, and I also showed some examples of how to use it. Before moving on to the proof, I'm going to think a little bit and do some rough work to justify how I came up with the main idea of the proof. This is the hypothesis that the limit of the quotient of f over g as x goes to infinity is L. Intuitively, what this means is that when x is very large, f of x over g of x is approximately L, is close to L. And this justifies the conclusion. Let's say, for example, that f of x over g of x is about 3. That means that f of x is about 3 times g of x. And given that whether an improper integral at infinity converges or not only depends on what happens for large values of x, if for large values of x, f of x is approximately 3 times g of x, it makes sense that if one of the integrals converges, then so does the other, and if one is infinity, so does the other. But I want more than that, I want a formal proof. So let's use the formal definition of limit. Here it is. We know that for every epsilon positive number, there exists a real number m, such that if x is greater than or equal to m, then the distance between the quotient and L is less than epsilon. Let's focus on the inequality at the end. I'm just manipulating these expressions for now. That inequality means that the quotient is between L minus epsilon and L plus epsilon. And I'm going to separate this in two parts. On the one hand, I can interpret this to mean that f of x is less than L plus epsilon times g of x. And on the other hand, f of x is greater than g of x times L minus epsilon, because everything is positive. So when I look at them this way, if I think for a moment of L plus epsilon and L minus epsilon just as constants, just as numbers, then this suggests that now I can use the basic comparison test in both directions, because up to a constant multiplying, which does not change convergence, then g is greater than f and f is greater than g. All I need to take care of is I need to make sure L minus epsilon is positive. Well, I can pick epsilon to be L over 2, and then L minus epsilon will be positive. And I get to pick epsilon because my hypothesis is that I know that the limit at the top exists and is L. So the statement in the second line is true for every epsilon, in particular for my choice of epsilon. All right, so these are all the ideas I need in the proof. So let's write it down. I begin by saying that since f and g are positive, we know that each one of the two improper integrals is separately guaranteed to be either convergent or infinity. Now, I just need to prove that one is convergent if and only if the other is convergent. Based on the rough work I did, I'm going to take epsilon equals to L over 2, which is a positive number, in the definition of the limit of the quotient is L. That tells me that there exists a real number m, such that whenever x is greater than or equal to m, then the distance between the quotient and L is less than L over 2. And like I did before, this inequality transforms into this. For every x greater than or equal to m, the quotient is between L over 2, which is L minus epsilon, and 3L over 2, which is L plus epsilon. I just wanted those two numbers to be positive. Now, this is only true when x is greater than or equal to m, but I go on to argue that that is enough. And here is why. For any function, I can write the integral from a to infinity as the integral from a to m plus the integral from m to infinity. But the piece in the middle, the integral from a to m, that is just a number. That never gives me trouble. The function is continuous there, it's integrable, it's not improper, that's just a number. It is only the other two, the integrals that go to infinity, which are defined as limits, which may or may not exist, which may be convergent or divergent. But the part in the middle is just a fixed constant. So what this means is that the integral from a to infinity is convergent, that limit exists, if and only if the integral from m to infinity is convergent, that limit exists. So at any place where I'm wondering whether one of the integrals starting at a is convergent, I can just pretend it started at m and nothing happens? The values of the integrals will change depending on whether I start at a or at m. The value will change, but whether it is convergent or divergent will not change. Okay, so I'm ready now to complete the proof. Now with all of this, I need to prove that if one is convergent, so is the other, and vice versa. So I'll go into steps. First, I assume the integral from m to infinity, because I can, of g of x dx is convergent. Then I'm going to use this inequality, that for every x greater than m, f of x is less than the constant 3l over 2 times gx, and that's just a constant multiplying. Now I use the basic comparison test, and since the integral of the bigger function is convergent, then the integral of the smaller function f must also be convergent. Reciprocally, I assume that the integral of f, starting at m, is convergent. I use the other inequality. For every x greater than or equal to m, then f of x is greater than g of x times a constant. And then again, by the basic comparison test, since the bigger integral is convergent, so is the smaller. And that completes the proof. We are done. To finish the video, however, I will leave you with two questions. Here is the theorem as we've understood it. Now, there is actually an expanded version of the theorem. In this case, we assume that the limit of the quotient exists and is a number, so not infinity, and the number is strictly positive. But what happens if the limit is equal to 0? Now, in this case, we can no longer conclude that the integral of f is convergent if and only if the integral of g is convergent. That would be a lie. However, there is still a conclusion to draw. There is still a theorem in here. So my question for you is, what can we conclude in this case? What will be true? Basically, it's half of what we concluded earlier. So can you complete the statement of the theorem? If you look at the proof, it reveals which half. Or, here is the other expanded version. If we assume that the limit is now infinity, then what can we conclude? Again, not the same as before, but there is still a theorem here, there is still a conclusion we can draw.